We're going to be talking about something called Ohm's law. Let's talk about voltage first of all. It says, fill in the following key facts about voltage. What was the definition of voltage? We said that voltage was the amount of potential energy that each charge has. Oh, and I usually put the wings on the capital V so that you could tell it was an uppercase V and not velocity. Well, if voltage is how much energy each charge has, energy per charge, what would its units be? Well, volts is joules per coulomb. What was the other word for voltage that kind of made it confusing? It started with the letter P. Potential, not potential energy, just potential. And for a change in voltage, we called it a potential difference. Well, in circuits, for current to flow, there has to be a potential difference, a difference in the voltage. If you have two items that are at the same voltage, no current will flow between them. So what exactly happens inside a voltage source? Inside a voltage source, there is some, by the way, we're going to be looking primarily at direct current coming from batteries, but most of what I teach you, if you do go into electronics, will work for alternating current as well. It's just a little more complicated. Inside a voltage source, there is some kind of chemical reaction going on. And really what that chemical reaction is doing, good morning. Pause the video for a second. Is done in separating charges. In the same way, Owen, that you can do work against gravity by lifting an object up, and now you've stored potential energy in that object, and when you let it go, it'll drop down. In that chemical reaction, charges, positives and negatives, are separated from each other. That's work. So you can kind of think as a battery as the equivalent of a human being lifting a mass up, but instead we're giving charges potential energy by, I'll use air quotes, lifting, say, positives away from negatives. And then when you let them go, they'll fall. There's a circuit symbol for a voltage source. So if this is a battery and if that's the negative terminal and this is the positive terminal, we use a short line for the negative and a long line for the positive. We'll be doing a lot of circuit drawings or analyzing a lot of circuit drawings. So right here, I see a battery, I see a resistor. That's a circuit drawing. So to help us understand what's happening in electric circuits, it's helpful to have a mechanical analogy. And Paige, the analogy I'm going to flog to death for this whole unit is I'm going to argue that every circuit can be thought of as a ski run. You gain energy from the battery in the same way as a chairlift brings skiers to the top of a ski run. A battery charges gain voltage. At a chairlift, people gain height, gain potential energy. Then, how do the people lose potential energy? They have to ski down a ski run. How do the charges lose that? Because remember, voltage is energy per coulomb. How do they bleed off their energy? They have to go through a resistor, and that resistor has to reduce them back to a voltage of 0. In the same way, the ski hill has to get you back to a height of 0 before you can get back on the chairlift. So my gravitational analogy of voltage, which is energy per charge, is kind of like height, which is energy per mass per gravitational field. The units don't quite match, but they kind of do. So let's suppose that this was a, just for giggles, 120 meter high hill. How many meters would you need to lose to get back to the bottom of the hill then? Be very, very obvious. So we would say this is a height loss of 120 meters. Let's suppose, again, just for giggles, this is a 12-volt battery. How many volts must the charges use up? How much energy per coulomb must be bled off going through this resistor if the charges can get back to the bottom of the chairlift? Be blindingly obvious. There, that's circuitry in a nutshell. We're going to get more complicated than that, but that's the idea of a circuit. So potential voltage is like height. Positive charges want to fall downhill in the same way a ball wants to roll downhill. The potential energy for gravity, mgh, is like the potential energy for electricity, qv. The only reason the v doesn't have a constant like little g in front of it is just because of how we define the units, and also because there aren't different gravity. We just define the units that way. So it works. Now let's talk about electric current. What happens if we connect a wire to one side of a voltage source? So here's a voltage source. Well, like charges, and so a few extra negatives will get repelled and go onto that wire. But as soon as that wire achieves the same voltage, the same energy per coulomb as what's in the battery, nothing's going to happen. Basically, no current will flow. I lied a little bit. Technically, a few electrons will make the jump, but very quickly, nothing's going to happen. What if the wire forms a continuous loop? Well, now electrons can travel and get to the positive. Now we're going to have a whole bunch of electron flow. And this presents us with a problem, specifically in this circuit here. If we were drawing this as a circuit diagram, it would look like this. And here's the problem. Every charge that leaves the battery has voltage, has an energy per coulomb. And it has to lose it all by the time it gets back to the bottom. Otherwise, it can't get back to the bottom. Where will that energy go? Well, if there was a resistor, the resistor would bleed off that energy. The little electric motor, the light bulb, the iPod, whatever you're plugging it into. Is there a resistor? Energy's got to go somewhere. So what's the problem here? Energy goes into heating up the wires. That there is a very dangerous circuit. The energy's got to go somewhere. You're going to heat up the wires. Heating up wires is a bad thing. So why is this a better circuit? If I were to sketch this, we now have a resistor. If we have, for example, a 12-volt gain from the battery, we would lose 12 volts in the resistor. That's a bit of a fib. We would in real life lose also a tiny bit to the wires because wires have some resistance, but Danica, it's going to be close enough to zero. We're going to pretend our wires have no resistance. Okay. So electrons need a completed circuit for current to flow. Put your pencils down, look up. Any of you ever touch an electric fence? Okay. Zach is smiling with some kind of odd, embarrassed remembrance. We won't ask. We'll choose not to.
Ever held onto an electric fence? It hurts. Farmers use electric fences to keep cattle in and foxes out. If an animal touches the fence, it gets a shock and it runs away. Today, by holding on to this fence designed to shock horses, the Brainiacs are going to learn all about electricity. This Brainiac is going to touch the fence and get an electric shock. This happens because...
Does the electric shock from an electric fence have some pretty good kick to it? Yeah, it kind of almost feels like you're getting punched. It's like, wow.
When he touches the fence, he completes the circuit between the live wire and the ground.
So when he touches the fence, the current flows into him, through his bare feet, into the ground, back to the electric fence mechanism, and now you've got a complete circuit.
The charge goes from the fence itself into the Brainiac, through the Brainiac's body and down into the ground. Then he goes along the ground into the earth stakes, along the earth wires, back into the unit to complete the circuit. Ouch! That hurts. Okay, he's getting pretty fed up now. So what happens if he stands on these polystyrene tiles? Brainiac?
What will happen now if he touches the fence? Standing on some styrofoam. Is styrofoam an insulator or a conductor? And so? No current will flow because it's like that very first picture I showed you of the single wire attached to the battery. A few electrons might jump, but very quickly he'll be at the same voltage as the wire itself. He won't feel a shock.
Touch the fence. The electricity won't pass through the Brainiac's body because it can't go through the polystyrene tiles to the ground to complete the circuit because they're a good insulator, so no shock. Off the tiles. Shock! On the tiles. No shock. Off the tiles. Shock.
So, most electric fences don't run continuously. That would be a huge electric bill. They pulse. I don't know if you noticed that. If you actually hold on to it long enough, you'll see shock, no shock, shock, no shock. They pulse. And so, in theory, if you jumped at the right time and timed it well, in theory...
Every time this light flashes, the charge in the fence. Now, if the Brainiac's feet aren't touching the ground when it flashes, he shouldn't get shocked. So if he can jump at the right moment, he'll be fine. Brainiac, are you ready? Excellent. On. Look, grab the fence. Do when I say on, be in the air. Here you go. On. Do you have no sense of rhythm? It's not difficult. You need to work on your timing. Or maybe we need to work on that theory a bit. What's better than shocking a Brainiac? Shocking a whole load of them. In you go. All our Brainiacs have bare feet and they're holding hands. Now, what will happen when the Brainiac at that end grabs the fence? It might just go straight through into the ground. It might make it all the way to here. Will this Brainiac even feel it?
Will the person on the end get a shock? Darman's not convinced me. We're sending charges through there. It's possible that all the charges will have leached into the ground by the time the third person, or by the fourth person. It's possible no charges will actually make it to the fifth person because they're always looking for the path of least resistance to get back and complete the circuit. So I don't know.
Who knows? Let's find that. Brainiac, on the count of three, grab the fence. 1, 2, 3, go. Hang on, sir, you haven't even moved. How far did it get? It got that far. Rate that out of 5. 1 to 5, how much did it hurt? 2. 1 to 5, how much did that hurt? 4. Right. Change order and let's do it again. Hold hands. On 1. 3, 2, 1, go. You didn't feel it at that end. So earthed by now. His eyes are still spinning. It seems that the current has never got past this brainiac here. So maybe it has unique insulating properties. Who knows? There's only one way to find out. Stick them on the end. On you go. You go and grab the fence. On my hand. Ready? 3, 2, 1, go! Whoa, now that went further! Where did that end up? Did you feel that? They went as far as that brainiac there. It's killed that brainiac. That's quite impressive. Right, new theory. What happens if we insulate using these polystyrene tiles all the brainiacs along the line, apart from the one at the end? Maybe the current will make it all the way. Let's find out. Insulate yourselves, brainiacs.
Now, the first four in a...
What is going to happen if 4 of them are standing on insulation, but the 5th person on the end isn't? Is that a completed circuit? I think now all 5 of them are going to get shocked. Yeah, it's going to go through everybody because it can't leach into the ground from the first person, second person, third person. I think all 5 of them are going to get the full effect, as opposed to it was trickling down earlier, so the person near the end wasn't getting as big a shock. Yeah.
So if you wanted to jump an electric fence, what if you wore like styrofoam gloves? Would you get shocked?
As long as you didn't touch it with the rest of your body, yeah. Yeah. But you're going to be touching it with the rest. Like, first of all, jumping an electric fence, are you talking like one that's, maybe a meter high? Or are you talking a chain link fence with a bunch of rungs? Because those also, there's no way you could climb that. So, but jumping, yeah. Yeah. Nope.
Ever held on to an electric fence?
I think that because they're insulated, they won't get a shock.
And on my count, touch the fence. 3, 2, 1, go. Wow! Well, that really works. Because you're insulated, it earthed here, so for the first time, the current made it all the way to the very end. You all got a shock, and that looked quite severe. Yeah.
Because they were all holding hands, the current travelled along the line to find the earth via our uninsulated brainiac, giving everyone along the way a shock.
Well, final experiment. What happens if you're insulated as well? Then you're all insulated. Okay, so join hands, please, brainiacs. And
If they're all on styrofoam, what will happen?
on my count, grab the fence. 3, 2, 1, go.
3, 2, 1, go.
Well, look at that. That's amazing. Nothing because you're all insulated. That's very clever, brainiacs. I hope you enjoyed learning about electricity. Well done. Good effort. That's what I say. Some people never learn.
Do be cautious around electric fences until you absolutely know the voltage and whether... there are some electric fences, like the ones that are used for cattle and things, that are designed not to be fatal, but there are some that are, so don't mess around with them. We get shocked in complete circuits all the time. You just don't realize it. Your skin is a pretty good resistor. It's a pretty good insulator. And so charges will flow on the outside of your body to complete a circuit all the time. And I can prove that to you. I need a couple of volunteers, maybe someone who arrived late for class. Voltage, the amount of energy per coulomb. Now we're going to talk about current. The symbol for current is a capital I, and it's defined as the rate of flow of charge. Anytime we talk about the rate, we're dividing by time. And what's our symbol for charge? Current is actually coulombs per second. It's sort of like velocity in our kinematics section. Except 1 coulomb per second, we name that an amp, named after a scientist whose last name was Ampere. So current is measured in amps. By the way, any charge Q is related to a certain number of fundamental charges, electrons, 1.6 times 10 to negative 19, negative if it's an electron, positive if it's a proton. So you can actually, from the current, figure out how many charges have moved through a circuit in a given time. A 1.5 volt AA cell is rated at 0.750 amp hours. Amp hours is not an SI unit, but it's used all the time in the electric industry because it's a really convenient unit to do math with in your head. Amp hours. Well, let's come back to that. When connected to the motor in a portable CD player, boys and girls, once upon a time, we used to listen to music on these round, shiny discs called CDs. And we used to actually carry, hanging on a lanyard on your waist or over your shoulder, a portable CD player. And that's how we used to listen to music when I was, middle-aged. When I was in my 20s, that was the cutting-edge technology. When I was a child, it was the Walkman came out when I was a teenager. Okay. And I guess when we hook it up, the cell provides 0.250 amps of current. Okay. Kai, what's A want me to find? What's our symbol for charge? You know what? Q is current times time. And this is why we have the units amp hours, which again are not SI units, but they're used in the industry. This is current times time. It's just so much more convenient not to think in seconds. So this is going to be 0.750, but this is amp hours. I need to somehow convert this to seconds. How am I going to do that? Well, how many seconds are there in 1 hour? I thank you, someone, for remembering. (2,700 coulombs of charge). So the amp hour unit, I'll come back to it in a second. It's really, really handy. I have a boat, and on there I have a battery that has 110 amp hours. Here's what that means. I can run a 1 amp appliance for how many hours? 110 hours before I need to recharge. I can run a 4 amp appliance for whatever 110 divided by 4. It's a really quick way for you to figure out how long you can be off the grid before you need to go plug back in and start recharging your batteries. So it's not a unit I'm going to give you on a test. I'm including it here, though, because if you get into electronics, or if you buy a trailer, or if you buy a boat, or if you just do any kind of wiring where you're running off a battery, and that's going to become more and more prevalent in the future as people go off grid, that's the unit they'll almost always talk about. B. Xavier, what does B want me to find?
How many electrons are stored in the cell?
Well, how many coulombs are stored in the cell?
2,700.
What's the charge on 1 electron?
Negative 1.6.
We'll call it positive.
1.6 times 10 to the negative 19.
How can I figure out how many electrons? You know what? It's going to be the number of electrons is the charge divided by the elementary charge. It's going to be 2,700 divided by 1.6 times 10 to the negative 19. Why didn't you put a negative? You'll see why. We're going to do something a little fast and loose with circuitry to make our lives easier. We're going to pretend things are all positive because it makes the math nicer. Divided by 1.6 times 10 to the negative 19. And I get 1.6875, so 1.69 times 10 to the, was it 22? I guess the unit for electrons would be electrons. Really, A and B are trivial. Like, it's interesting to me as a nerd, George, but if you're actually designing a circuit, C is the question you want the answer to. George, what does C want me to find? How long will the cell power the motor? Okay. Well, if current is charge over time, get the time by itself. We have 2,700 coulombs of charge. How many amps is this specific device pulling? How many amps? It tells us how many amps is it pulling. No, read carefully. When connected to the how many amps? Yep. This is what you would like to know. How long can I run this before the battery dies? What do you get? You get 10,800. And again, what units is that? This is our standard unit for time, which is, nobody thinks that way. That's why in the industry, they'll do everything in amp hours, but in physics, we'll use amp seconds and seconds, because that's the SI standard. So 10,800 seconds. Divide that by 60. How many minutes? Because that's really what you'd like to know. 180 minutes. Divide that by 60 again. How many hours? Okay, so I have to recharge in 3 hours, or swap batteries out in 3 hours. Okay. Next page over. Let's go back to my ski hill analogy. So in my ski hill analogy, I already said that chairlift was the same as the voltage increase. So I'm going to think of the battery as the equivalent of a chairlift. A battery gives charges more energy per coulomb. A chairlift gives humans more height per gravitational field. Okay, what's the analogy for current on my ski lift? The flow of charges in a circuit, which is coulombs per second, it's like the number of skiers on each ski run up and down the mountain. It's how crowded the mountain is. Bigger current, more crowded ski run. Smaller current, less crowded ski run. Now, this is where the analogy breaks down a little bit. In a circuit, electrons flow at a constant speed. So we're going to pretend all the skiers on my ski hill analogy are all skiing at the same rate. They're using their skis to control their speed. Nobody's going faster. Nobody's going slower. Everybody's going single file. That's what we got. Okay. There's a bit of a problem here. And this is going to explain why when you said negative 1.6, positive, in a circuit in real life, it is the electrons that flow because the protons are locked in the nucleus. They go from negative to positive. It would be much nicer, Zach, if we could imagine a circuit going downhill from positive to negative. Then we can think losing energy by going from a higher voltage to a lower voltage instead of having to flip everything. So we're going to pretend. We're going to define current as the direction positives would move if they could. And we're going to argue, Danica, you know what? An electron moving one spot to the left, mathematically that's identical to a proton moving one spot to the right, even though the proton's not moving. Mathematically it's the same. So we're going to define current, often called conventional current, as from positive to negative. Even though that's not what happens in real life, it makes the math way easier. Okay? So we would like to be able to say that current flows downhill from a higher voltage to a lower voltage. This way. For this reason, we're going to focus on the positive charges, the nuclei. The uphill flow of electrons, this way, which is more counterintuitive, is mathematically equivalent to the downhill flow of positive charges. So what we call current, then, is actually the downhill flow of positive charges. Some textbooks or some electric manuals will call this conventional current because, Paige, it's a convention. We just decided, let's let current be from positive to negative, even though that's not what happens in real life. So, example 4 says this. Draw the direction of electron flow. I'm going to do electron flow for me in red. Electrons flow from negative to positive because unlike charges attract, electron flow would go that way. Counterclockwise, if you all know that, having grown up digital, I don't know if you know what clockwise and counterclockwise is, but conventional current, which I'm going to do in blue, would be from positive to negative. and the symbol for current is a capital letter I. Again, it's much nicer to imagine charges go up the chairlift, gaining energy, lose energy through the resistor, as opposed to electrons going this. Yeah. That brings us to Ohm's law, named after a scientist whose last name was Ohm. Every circuit offers some resistance to the flow of charge. The circuit symbol for a resistor is a series of short-angled lines I wrote here, which you should recognize from Science 9 or Science 10, or maybe not, depending on with COVID, plus or minus whether or not they got to it. Resistance is due to, let's call it electric friction. Now we're going to talk about electrons moving again, even though we're pretending it's protons moving. But when electrons move through the wire, they bump into stuff. They collide with the atoms of the material they are passing through, and as they do so, they can lose energy. This energy is given off as heat. It heats up the material, and we're pretty good at bleeding that heat off and getting it to power stuff. A loss of energy implies a loss of voltage because, voltage is energy per coulomb. A voltage drop. Now we're going to talk about the protons, pretend it's positive. So here's what we would say. Let's suppose right here we have a higher voltage, 8 volts. And let's suppose right here we measure 3 volts. Be obvious. How many volts must we have lost going through that resistor? That means every coulomb of charge bled off 5 joules of energy, because voltage is the amount of energy per coulomb. 5 joules for every coulomb of charge that goes through there. 5 volts.
-5 volts.
That's a great question. Technically, yes. We're going to get lazy shortly, and because it's always a voltage drop, we're going to stop putting the negatives and we're going to stop putting some change-ins, and we're going to streamline our notation just because, let's stop writing the obvious. So the amount of flow through the circuit, current, depends on the amount of resistance and on the voltage applied. What can be said about the current flow in each case? Fill in either large current, I'm going to do big I, or small current, little I. High resistance. Okay. For high resistance, I imagine a really narrow hallway in our school, because it's really tough to get through. It's high resistance. Will more people fit through that hallway, or will less people fit through that hallway? So, smaller current, or we can say current will decrease. What about a low resistance, the wider hallways? So the first thing I want you to notice is that when resistance goes up, current goes down. What that means is, as an equation, resistance must be in the bottom of a fraction, because when it gets bigger, current gets smaller. What about voltage? Well, what was my analogy for voltage? A ski hill. What's more popular, bigger ski hills or bunny hills? So when voltage goes up, current goes up. When voltage goes down, current goes down. You know what? That means it's on the top. That's Ohm's law that relates voltage, current, and resistance. Except it's more commonly written this way. V equals I times R. And they're all capital letters. How many of you have seen that before in Science 9 or Science 10? V equals I times R. Okay. So a few of you have. It's on your formula sheet. Worth memorizing, but Paige, you'll memorize it out of laziness because we're going to be flogging it to death for the next few weeks. Technical, going back to Aiden about negative. First of all, because it's a voltage drop, it's technically a change in. I'm going to be sloppy, and nobody does that. We just know it's a change in because you lost voltage going from here to here. So it should say delta V equals I times R, but it's cumbersome, and so for this reason the delta is dropped. But when you see it, you should think of it as a voltage change or a voltage drop or a voltage gain. What are the units for resistance? Ohms. So current is measured in amps, coulombs per second. Voltage is measured in volts. That's the easy one. Joules per coulomb. Current is measured in ohms. 1 ohm of and the symbol for ohms, that. The Greek letter omega. 1 ohm of resistance means that a voltage drop of 1 volt will result in a current of 1 amp. Good conductors have low resistance. Poor conductors typically have high resistance. Poor conductors, insulators, have high resistance. You don't need to memorize these. We're going to do a little mix and match. Over on the left, I have a bunch of stuff. On the right, I have some typical resistances. We're going to see if we can just puzzle our way, just to give you an idea, Owen, of what's a really big resistance and what's a really small resistance, so that you have a ballpark figure if you're trying to crunch some numbers. Out of these 6 things, which one does not admit electricity at all? Which one would have an infinite resistance? Which one of those is an insulator? Metal wire, light bulb, electric motor, human skin, lab resistor, or piece of glass? Glasses. If you look on power lines, the big ones, the metal tower ones that run across mountains, those black things that the wires run through, there's some kind of glass ceramic material. Otherwise, the power would drain through those metal power lines. So what's the resistance of a piece of glass? Pretty much infinite. I mean, if you bump up voltage and current enough, you can probably get some to go through. And now your phones have a type of conductive glass where they've mixed certain trace elements in there, but generally glass is an insulator. Let's go in the other direction. Which of those remaining do you think would have the lowest resistance, would be the most conductive? Yeah. Let's cross out ones as we use them. Copper wire ideally would have no resistance. Well, we'll say 0.1 ohms. Okay. Of the ones remaining, which do you think has the highest resistance? Human skin. Okay. Now we have 3 remaining. Of the 3 remaining, which of these do you think gives off the least amount of heat? And because it's giving off the least amount of heat when it's running, therefore it has a pretty small resistance. Do light bulbs give off heat? So it's not a light bulb. Electric motor. Ideally, you want an electric motor to have very small resistance. So it would have a resistance of about 5 ohms, ideally. A light bulb with very thin wire would probably have a resistance of about 2200 ohms. And a standard lab resistor, if you're playing around with circuits, usually has a resistance of around 200. I got into last year, last quarter, I had my prep, so I was only teaching half time. And so I started to get into electronics and circuitry. So I bought a bunch of electronics kits. They're in those boxes over Terran's shoulder on the counter. And they have a whole bunch of little tiny resistors labeled 1 kilo ohm, 1000, or 2 kilo ohms, or 10 kilo ohms. So they also have a lot of resistors in thousands of ohms as well. Little technical comment. Again, we're going to make the math nice. Actually, as a circuit heats up, as we're pretending protons move. As the imaginary protons move through the resistor, they cause it to heat up, and by doing that, the atoms move faster, and by doing that, the resistance changes. We're going to pretend that doesn't happen. We're going to pretend all of our resistors are constant. Another technical comment, although human skin is a good insulator, typically tens or hundreds of thousands of ohms, it will only protect us up to a certain point. When the voltage exceeds a certain value, the skin will break down and ionize in the same way lightning could ionize air, current can ionize your skin. And once on the inside, we're basically salty water, and that conducts electricity pretty well. So, what's the danger of electric shocks? Well, two effects. First of all, if you're getting a big current, there's the heating up of tissue as electricity flows. This can cause severe burns and destroy internal tissues and organs. This is probably what you think of about when somebody was electrocuted, they got burned. But there's a more subtle danger. The body runs on electrical impulses. Your nerves and your organs run on electrical impulses. And so a fairly small current can actually affect your body's ability to control its own muscles. And when those muscles are your heart or your diaphragm for breathing, that's a bad thing. So once beyond the skin, the heating effect grows larger with larger currents. You need a pretty big current to burn and electrocute yourself. But the current required to cause your heart to fibrillate is only about 100 milliamps, 0.1 of an amp. Not much. It's often nicknamed the death current. So be careful when dealing with electricity. That was a long story to say, don't muck around with electricity unless you really, really know what you're doing. Next page. Let's go back to our ski hill analogy then. We're going to say that resistors are like the ski slopes where people, charges, lose energy to get back to the bottom of the chairlift. And we're going to say, if you're looking for an analogy, the amount of resistance, that's kind of like how deep the snow is. Deep snow means slower skier flow. You can't get as much current through it. High resistance. Low resistance, hard packed snow, people can go, you can get more skiers on there. Or you can kind of think about it as how wide the ski slope, the ski hill is as well. So high resistance, very narrow trail, you can't get many skiers on there. Low resistance, wide trail, you can get a lot of skiers on there. So what does Ohm's law for ski hills state? It says the flow of skiers' current relates directly with the height of the mountain. Higher ski hill, more skiers. And inversely with the depth of the snow. Smaller or more narrow trail with deeper snow, can't get skiers on there as fast. Example 7 says find the current in each case. So typically when we're solving circuits, we'll think or write V equals I times R. Eventually you'll just think that, but let's write that. Paige, what's example 7 wanting me to find? What letter was current, V, I, or R? How would I get the I by itself then? How will I move the R over? So, I equals V over R. I equals V over R. In the left-hand circuit page, what's the voltage that we're getting from the chairlift? So how many volts are we losing through here? You know what? Also 6 volts, because it's got to go. Okay, so it's going to be 6 divided by 25, which is what? Is there a good way to divide by 25? Divide by 100 and multiply by 4. Is it 0.24? Okay. What about on the right-hand side? Well, because there's no resistor, that voltage is going to get used up in the wire. The energy per coulomb's got to go somewhere. And so we're going to have 6 divided by 0.001. How many amps of current will be flowing through this circuit? Now, if this is a battery, remember, current is also the amount of coulombs per second. We calculated that one battery held about 2,700 coulombs. You'd drain this battery dead pretty quickly if you hook this up. It would be bad for the battery. You'd wreck it. You'd probably, within about 5 seconds, have completely destroyed it. If this was an unlimited voltage source, not a battery, you're heating up the wires. Fire bad. These would heat up red hot. Here, this would drain the battery at a much slower rate, only 0.24 coulombs every second. This device would run for a while, and the wires are not going to get very hot. This second one is an interesting one. It's called a short circuit. A short circuit is a circuit that has no external resistors, where the only resistance is the wire. Your stove elements are a controlled short circuit if you have an electric stove. That's designed intentionally, very carefully, but it's a short circuit. So sometimes there are certain situations where you want them, but the vast majority of the time, fire bad. You don't want them. So it has a very small resistance. You're going to get a very large current. Of course, it depends on the voltage source. If you short a AA cell using lab wires, you'll quickly deplete the cell, but you're not going to do any damage. If you short your car battery using lab wires, the car battery has enough charge stored to make the wires hot and possibly even melt them. If you short BC hydro with a lab wire, because that has an unlimited source of charge, that's a bad thing. Well, no. What we do is we have a circuit breaker that will trip, or you'll blow a fuse, which is just a thin wire that will melt. As we'll see in the next lesson when we look at power, large currents means that wires can get hot and melt, causing an electrical fire. So again, be careful with electricity. Nearly done. Good. Last thing I want to talk about is how we measure voltage and current. I'm going to pause the video for a second. So Zach, consider the following circuit. Here's the real circuit, a 6-volt battery running a light bulb. We would draw it like this. First of all, right here, which way is current flowing from the battery, up or down? Which way is current flowing from the battery, up or down? We said which way the positive, so we would say this. That's which way the current is flowing. Electrons are flowing down, but we're going to pretend that's not happening. Okay? If I want to measure current, the number of skiers, what if I decided to measure the current by attaching a wire here, putting a little gate right here, and attaching a wire here? Don't write that down. And attaching a wire there. This would not work. And the reason is, a bunch of skiers would go through this ski run. I would have no way of telling or counting them because they didn't come through my gate. To measure current, what you have to do is physically break the circuit somewhere, and you need to install your current measurer in the circuit. So let's scroll down. This is what we're going to write down. If I wanted to measure the current going through this circuit, the current, we call it an ammeter. It used to be called an amp meter, but amp meter was tough to say, so we dropped the P. It's an ammeter. It's measuring current. You have to measure current by wiring it in series. There's going to be a whole lesson on that word later. But if I'm going to measure current, I have to physically force all the skiers to go through my ammeter. What about, so this is correct. This will be incorrect. Skiers could go through there, and there's no way I could count them. What about for voltage? If I wanted to measure how high this hill is, in the same way, next page over, that I'm unable to measure Aiden's height from a single location, I have to decide where the top and where the bottom is. For a voltmeter, I have to wire that in parallel. If you're ever using a multimeter or a voltmeter, you'll see it has 2 prongs, and you have to touch the prong to one location in the circuit and another location in the circuit, and it's telling you the change in height, the change in voltage between those 2 locations. In the same way as if I wanted to measure Aiden's height, I would have to have something on the top of his head, something on his feet, and measure alongside him how tall he is. So this would be wired correctly. This would not measure a height. This would not measure a change in voltage. This would not measure it. This would not work. And again, more on the word parallel in an upcoming lesson. Final technical comment. We focused my introduction here on direct current, DC. It always flows in the same direction. It has a constant value. Much of what I've said also applies to alternating current, AC, but it has a magnitude that varies as a sine function. Alternating current looks like this. And it has a direction that's continually changing. The AC power that BC Hydro delivers to our homes has a frequency of 60 hertz. That means it changes directions 60 times per second. Sorry, 120 times per second, because it's changing direction. And the voltage amplitude of 110, it's actually 113.4, I think. It's actually, you know what, we often round it to 120, because 120 is a nice round number to do math within our head, and those extra few volts aren't going to make a big difference unless we're designing like microchips or something like that. So we're going to use 120 volts AC for simplicity, also because 120 volts and a frequency of 60 hertz gives you some nice math you can do when you dive into AC circuits. We'll look at AC circuits a tiny bit, but I'm going to be teaching you how to solve direct current circuits. What's your homework? Study for the test, but number 1 is good, number 2 is good. Three is good. We're going to skip 4. 5 is good. 6 is good. And we'll just assign that little bit there. Not too much homework. Okay.